Okay, welcome folks. We are going to look in this video at the Van Hiele phases of learning. Now what the phases of learning is referring to, we first looked at the Van Hiele levels of geometric reasoning, of which there were 5 levels, starting at level 0, finishing at level 4. But the phases of learning informs teachers, informs the educator of what is necessary to do when you teach from one level to the next, to afford learners the opportunity to progress to the next level. The phases of learning does not just apply to geometry. You will see as we go through them that there's more and wider applicability of the phases of learning. It should inform any good teaching that happens. Let's start. Before I start, I want to look at the characteristics of the levels of geometric reasoning. Very important to understand them. So, before we start with the phases, let's look at this. First of all, the levels are sequential and hierarchical. A learner or a student must master one level before advancing to the next. Okay, so you can't go from level 0, if the child is on the visual level in a class, straight to level 2 or level 3. There's a process that needs to be followed, and that process is activated through the phases of learning. Okay? The level advancement is based on experiences that are afforded to the learner, not based on age like Piaget's theory. So has a learner experienced what a proof is, how to construct a proof, how rigid a proof is constructed, and that you can't just say it is a right angle because it looks like one. What are necessary to argue things in geometry? If a learner hasn't experienced that, then you cannot ask him to be at that particular level where those characteristics come to the foreground. So it's sequential and hierarchical, and it is based on experience. That is challenging the notion that it is depending on the learner's age. Okay, students do not automatically progress. They gain abstraction and sophistication in their thinking as a result of their experiences, again coming as very important. Students may reason at multiple levels or at intermediate levels. So for that, the teacher must develop a trained ear to listen to the answer that the kid is giving, and not just whether the answer is correct or incorrect. Listen to what they are saying, how they achieved that answer. And that is very, very important. I've often, as an educator at a tertiary institution, come across my students where I go into a classroom and I observe their teaching during teaching experience, and I see, or they ask a question and the learners give the wrong answer and they go, no, what do you think? No, what do you think? Instead of working with those incorrect answers and asking follow-up question, well, tell us how you got to that answer. Because there might be more than one learner in the class that got the same answer. And if you as a teacher don't afford those opportunities in your classroom, your learners do not necessarily progress to the next reasoning level. So children advance at different rates and for different concepts. And you need, as a teacher, you need to be aware of that. That the class are not all going to come forward with you. There are some kids that are going to grasp it quickly, but then you as a teacher need to activate the thinking with those kids and walk the journey with them. Those kids that are not getting it the first time around, by asking questions and by listening to what they're saying. Now I'm deliberately saying these things because that's what the phases of learning is going to argue. Okay, so each level also has its own language. So it's your responsibility as a teacher to develop the mathematical register that is required at a particular level. Terms that are considered correct at one level may be modified at another. Now, if I think of a quick example here, in the foundation phase of learning, teachers often say that multiplication makes bigger and division makes smaller, for the child to understand what it does, to understand the product better. But once you enter the intermediate phase, grade 4 to 6, it's no longer cool or correct to say that, because now you work with fractions, and 6 multiplied by a half is not bigger than 6. It's all of a sudden smaller. 6 divided by a half becomes bigger. It becomes 12. Okay, so there's 12 half pieces in 6. So now all of a sudden division makes bigger and multiplication makes smaller. It's the only example I could think of now. But I think it's a good example to illustrate that point. Instruction and language at a higher level than the student may inhibit learning. So if you are functioning at the level of rigor in the geometry classroom, and a child is still basically trying to get out of the visual, there's no learning that's going to take place for that child. And that is why the phases of learning and a clear understanding about the phases of learning is important for teachers. So let's see. The Van Hiele's proposed sequential phases of learning to help students move from one level to a next, folks. And this is the expert knowledge, the professional knowledge that teachers have that are teaching mathematics and should have, so that you can help your learners progress through the levels. The first level is called the information phase, where you gather information about what it is the learners know, how well they know it, and at this point you listen. You're a facilitator, you're listening. Then you go into the second phase, which is guided orientation. And that's exactly what it does. You do not tell learners, yes, you're wrong, or no, you're right, or do this or do that. You guide them to orientate them towards what it is that you want them to think and to reason. Then you foreground what is important that they experience during the first two phases. What is foregrounded as important knowledge under the heading Explication. Then free orientation means they go and they apply the new knowledge to problems that you carefully designed as a teacher to bring them into the next level. And finally, the integration, where you take these ideas and you put them together, how they inform one another about the object that we are studying. Okay, so let's start. First of all, we learned about the Van Hiele levels. The Van Hiele levels, level 0 visualization, level 1 analysis, level, let me just move my face out of the way there. Level 3 was informal deduction, level 3 was deduction, and level 4 was rigor. Okay, dealt with rigor. Now, in their argument, the Van Hiele's are saying that in each of these levels, the phases of learning, information doesn't belong to level 1 and guided orientation to level 2 and so forth. In each of these levels, progression happens if you go through the 5 phases of learning that they are proposing. Okay, so let us have a look. According to the Van Hiele's, a learner progresses through each of the levels as a result of the instruction that is organized into the 5 phases of learning, folks. The 5 phases of learning are hierarchical. Okay, it starts with information gathering, then it goes into guided orientation, then into explication, and then to free orientation and integration. Okay, let's start with information. What do the Van Hiele's mean when they talk about the information session? Well, through discussion, the teacher identifies. There's discussion happening and there's identification. What learners have already come across related to a particular topic, and what learners and the learners become orientated then to the new topic. At this level of information gathering, vocabulary is clarified. The mathematical register is clarified and developed. Now we saw with the levels that the register is very important. It is level specific and needs attention from the teacher. So the teacher holds a conversation with the learners in well-known language and symbols in which the context he wants to use becomes clear. So at the information gathering, you might want to talk the idea of triangles because you need that knowledge to progress to the next theorem. So you ask questions. What type of triangles do we get? How do we classify triangles? What can we say across different shapes? The idea of congruency and similarity. How are they similar? What makes a congruent triangle similar? Can a similar triangle be congruent? And not evaluatively listening to gather information. Listen to what the kids are giving you, because that gives you something to work with. Good question. They have dealt with rhombi and squares and quadrilaterals through their teaching up to this point. So why it's called a rhombus? Why is it a rhombus? There's 4 figures that represents quadrilaterals that are regular. Why do we call them a rhombus? Okay, so information. The students should then freely explore and discover at this level. You create activities for the learners so that you can gather this information. Those activities might need some prompts, or might need a visual prompts or visual mediators, and that little paragraph that I spoke about in a previous video. But you want them to freely explore those materials and discover properties and structures at this level, at the information level. While students are exploring, the teacher observes and informally assess student thinking. You are a facilitator of learning at this level. You're not going to go in and say, no, you're doing that wrong. Why don't you look what Peter's doing and then do what he does? Or, no, Peter, you don't understand. Explain to Peter and listen. Listen to that explanation. Because while this explanation is happening, you are correcting language and you are orientating. You are working towards the next phase, which is guided orientation. Okay, so at the information level, children freely explore and discover through the activities designed by the teacher. The teacher observes and informally assesses and acts as a facilitator. What do students do? Well, they share and talk about the ideas encapsulated in the shapes or in the object that they are busy learning about. Okay, so students need to share and talk for the teacher to listen and to hear and to see where must I pitch my lesson. Always start a lesson with information gathering, folks. The cognitive hooks that you want knowledge to hook onto is very important. If there is none of that hooking happening, you are over the heads of the kids. They won't get it because you're skipping phases and you're skipping levels. So learners begin to see at this level how pieces fit together. They begin to discover the properties and relationships of figures that they're dealing with. Now, it's not just talking about pieces of manipulatives that they're using, it's pieces of information. Okay? How do those pieces fit together to provide the minimum and sufficient conditions for a shape to exist? Now, through the phases of learning, the Van Hiele's often referred to use of tangrams, which is mainly used at a primary level or at a junior secondary level. Okay, we don't use tangrams anymore when we get to the higher grades, grade 10, 11 and 12. Doesn't mean that you can't use them. If a child has not activated relational understanding in the geometry class yet, feel free to use whatever manipulatives you can bring into the classroom as a teacher to investigate understanding and to build relational understanding in geometry. With all of that now, and have listened and facilitated and gathered the information, we go into the second phase of learning, which is called guided orientation. Here, the activities guide the learner toward the relationship at the next level. Okay, now the activities guide. Okay, that is the activity, the physical activity that they're working with, but also the activities of the teacher. The way the teacher facilitates at the guided orientation, okay, level, or phase of learning rather. The relations belonging to the context are discovered and discussed by the learners. Now that would mean at the information level, the teacher have gathered information about what it is that the kids know. Now, obviously, folks, every year, if you as a teacher go through this phase, there's a certain level of expectation about what the learners know that you can work from when you design your activities. But the key thing here is, at the guided orientation phase, activities are designed to look at relational features that must be discovered and discussed by learners. Learners explore the objects of instruction in carefully structured tasks, such as folding, measuring, constructing, whatever it is that you as a teacher want to have and use in the class. An idea, for instance, is to use mathematical software, depending on which level you are teaching at. So if you are at a grade 11 level, you would have seen me in the previous video use geometric software to talk about the relational features embedded in certain theorems, and then the big ideas in maths. If I transform that point by moving it along a circle, which relationships remain invariant? Why do they remain invariant? And which relationships or characteristics are changing? So here you can use even folding. I think about grade 8 and 9. If we want to prove that the angles in a triangle add up to 180, cut out a triangle, tear those angles off, put them next to each other, and they must lie on a line. That is a practical way to see, but hang on, there's a point here. That is definitely true. And then constructing a proof. How do I construct a right angle? You can construct it through a folding activity. You fold a piece of paper along any line and then fold it again so that those two folds lie on top of each other. We're going to look at, I think there's an activity like that when we talk about habits of mind. So there's a lot of things that you can draw on here. As a teacher in the guided orientation phase, the most dynamic is the use of software. Now folks, just at this point I want to tell you that Geometer's Sketchpad is freely available online. You don't have to pay for it anymore. Download it and use it in class. Kids can download it on their phone. They can download it on tablets. If they have laptops that they can bring to school, they can download it on there. And you as a teacher can use it as a tool to teach with. Okay, so what does the teacher do at the guided orientation phase besides developing the very carefully structured tasks? The teacher ensures that learners explore specific concepts. Remember, this is not information gathering, this is guiding towards. If you want the learners to think about the angles and they are focusing on the sides of a shape, acknowledge the fact that yes, that is true about the sides, but have you thought about the angles? And walk away and get that conversation going. Okay, so you do that through carefully planned activities and facilitation strategies. Often we let students discuss things in groups, and the teacher stands in front of a class and waits. Okay, I'm going to give them 5 minutes to discuss, and then, okay, let's talk about what you discussed. No, you walk around, you listen, you're still gathering information, but the purpose of that gathering is to guide and to orientate learners. Okay, so activities are presented so that students' attention is focused on particular characteristics of shapes. Questions might be generated from the first phase, the phase where you gathered information. Choose 2 shapes. How many different shapes can you make with them? Now what that is referring to is the tangrams. Folks, if you don't know what a tangram is, please read up on it. It is an enormously useful tool in the geometry classroom, especially in the earlier grades. Use 3 shapes from the collection of tangram shapes you have to make a new shape. How many ways can you make that shape? Which pieces can be made from 3 other pieces or 3 other shapes in the tangram collection? Okay, these are questions that is on a carefully designed activity sheet by the teacher, and as the kids are busy with the activity, the teacher observes and listens and orientates. Have students record what they find by tracing possibly around the shapes and share with others. One activity will often lead to another in this phase, the guided orientation phase. Now folks, it's important that at this phase you do not say yes, you're wrong, or you're right. You guide and you orientate. You are facilitating the learning. If something is wrong, ask a question that activates the thinking with the learner, so that the learner can say, hang on, why was I thinking that? Of course it can't be. That's the reaction you want. But it doesn't come when saying, no, you're wrong. Think something else. Look at Peter, look at Mary, look at what I've got on the board. No. We say, hang on. Okay, so that's what you've got. Tell me how you got there. The child will talk, you listen, and you say, okay, you said that A is equal to B. Are you sure? What are the relationships that you're drawing on that makes you say that? And that activates the necessary relational thinking for the child in the guided orientation phase. So yeah, the teacher provides instructional activities in which students explore and discuss a concept, preferably in small groups, and come to consensus about that concept within their group. The teacher's role here again is to facilitate, provide hints, to scaffold questions, to guide and orientate learners, rather than provide answers and saying, yes, you're right, no, you're wrong. Okay, often a child in this phase will get so excited when they think they've got to a point that they put up their hand and say, sir, please, or ma'am, please come and look. And then you get there and what do you want me to look at? Am I right? My face, my whole body drops at that point. And I throw it back at the kid. I said, well, what do you think? What do you think? Do you think you're right? And they must probably reply, but sir, that's why I'm asking you. Say, well, I'm asking you the question. What do you think? How did you get to that answer? What makes you think it's right? Let's talk about it, not yes or no. It's one of the most pet hates of mine, is if I give learners something to do in a class and they want me to come over just to come and see whether their answer is correct or not. So an activity here again at guided orientation. Fold the rhombus on the axis of symmetry. What do you notice? Now you as a teacher knows the axis of symmetry of a rhombus is its diagonal. You're not going to tell the kids to fold it on its diagonal. You want them to discover that big idea in mathematics, that the diagonal in a rhombus is indeed a line of symmetry. And then based on that, what can I conclude about the properties of the rhombus? Now, I once was writing an analytical geometry chapter for my textbook, and I looked at all the properties that a rhombus has. There's 16 properties, okay, if I remember correctly. And those can all be discovered by activities. And then, once the activity has shown it, well, that could be a folding activity. It could be a cutout and folding. It could be an activity that the relationships, the minimum and sufficient relationships, are constructed using Sketchpad or GeoGebra or one of those programs, and then varying things in the diagram and seeing which relationships remain in place. Okay, but we do not want the child to, from the beginning, have the knowledge that the diagonal of a rhombus is a line of symmetry. Because why? Let's talk about that for a second. When you work with a parallelogram, that falls to the wayside. It's no longer a line of symmetry. Okay? But there's rotational symmetry on that mirror line, which is a line of symmetry of the other two regular figures, the square and the rhombus. Okay, so for explication, at explication, the teacher, that's our next level now. The teacher clarifies terms that the children are already using and introduces new terms. So at this phase, you foreground what is important about what was just learned. Students describe what they have learned about the topic in their own words, and the teacher introduces and corrects the relevant mathematical terms that the kids or the students are using. Okay, so remember explication. You've gone through the first listening phase. You've gone through the guided orientation. Now things are foregrounded that are important. Under the guidance of the teachers, learners share their opinions about the relationships and concepts that they have discovered. The teacher guides, the learners share what they discovered. The teacher listens. The teacher is still guiding and orientating to some degree, but also fixing mathematical register relevant to the phase of learning or to the level of reasoning. The teacher takes care that the correct technical language is developed and is used. Tasks and explorations that deliberately develop the vocabulary associated with the ideas that have been encountered so far are developed by the teacher. Your tasks are deliberate at this level. Now those tasks are given to kids at the guided orientation phase, and at the explication phase you foreground the knowledge that was important for them to learn doing those activities. So at the explication, questions provide opportunities for the terms to be used. So what shapes have a right angle? Which shapes have a right angle? How many lines of symmetry does each shape have? What is the same about the triangles that you're working with? What is different about those triangles? Which shapes have parallel sides? Now, we're talking across a family of shapes here, but you can see that here, specifically at the third level, level 2 of Van Hiele reasoning, where they start reasoning with properties of shapes, these type of questions are key, because it takes the minimum and sufficient characteristics, it highlights it as very important. And the collection or a certain relationships or characteristics being put in place in a shape results in a particular shape that we're working with. You discuss your ideas with a group and then with the whole class. And during that whole class discussion, it is where the teacher still listens, still guides and orientates, but makes sure that the knowledge that was important to move forward, the necessary and sufficient, is explicated, is brought to the foreground as important and developed together with its register. The diagrams lie on the lines of the diagonals. We're talking again about the rhombus. The diagonals lie on the lines of symmetry. Okay, so what other figures will have that same property? Now, you as a teacher know that the kite has that property. Equilateral triangle or even an isosceles triangle under certain conditions has that property. So those are the things you want the kids to go and discover with shapes that they possibly cut out and fold. There are two lines of symmetry. Where are those lines of symmetry? There might be along the two diagonals. There might be 4 lines of symmetry in a diagram. Which diagrams possess 4 lines of symmetry? The opposite angles are congruent. The diagonals bisect the vertex angles. So if a diagonal is a bisector of a vertex angle, in which figures do that happen? Discuss, classify, group those figures and their properties together so that learners can draw on the correct language and on the minimum and sufficient properties to argue shapes. Folks, for the high school classroom, this is exceptionally important at the level of analytical geometry, coordinate geometry. If we ask, prove that that figure is a parallelogram, what is minimum and sufficient to prove it? Prove that we're working with a rhombus, etc. Okay, so after the class has completed the guided orientation activity, the teacher leads the class discussion. Each group shares their findings, and through discussion, misconceptions are reconceptualized. Even if groups share the same conclusions, much can be gained when students hear explications or explanations formulated in different words from a slightly different point of view. Okay, so it's essential that learners are afforded that opportunity, the experience idea that the Van Hielens talk about, rather than at the right age. The Van Hiele model emphasizes that this step is often shortchanged in mathematics classroom at the expense of student understanding and learning. The explication phase, the feedback phase from the learners, and the teacher correcting language and reconceptualizing misconceptions are often not present in classrooms. It's not good enough to say, no, it's wrong. Why is it wrong? What properties makes it wrong? What relations will make it correct? Which relations are missing from what you explained? Sometimes students arrive at the wrong conclusion. During the discussion, these misconceptions can be corrected, especially if the students, or if other students rather than the teacher, are able to explain to their peers. Now folks, especially in environments that are where children are in competition with each other, often learner A, which is in competition with learner B, doesn't want to listen to what learner A is saying. As a teacher, you need to absolutely manage it very sensitively, but do not shut learner A down because learner B doesn't want to listen to him or to her. Afford everybody to contribute, because the more affordances that happen, the more experiences are provided to the learners. Then we reach our free orientation phase, where we're applying the new knowledge that was learned. This is the 4th phase of learning. At this point, the language is corrected, misconceptions are being addressed, errors were carefully but sufficiently negotiated, the language is fixed. Learners apply these relationships now that they have learned to solve problems and investigated more open-ended tasks. Again, the job of the teacher at this level is to design those tasks carefully. That highlights the knowledge that's important, the properties, the relationship. The relevant relationships are known. The moment has come for the learners to work independently with the new concepts using a variety of applications. Activities and problem-solving tasks can be completed at this level or in this phase in different ways. Now, folks, I just want to draw us back to the definition issue that Van Hiele and Freudenthal spoke about. If we went in and we said, okay, today we're learning A, B, and C, and you put A, B, and C on the board, you talk through it, give examples, now go and practice. You're not going through the phases of learning. That comes with a huge assumption that's often incorrect and at the cost of learning, that the learners are at the same level and that they know and understand and can function at that particular level. So at free orientation, the aim is to apply what they've learned and become more skillful. How many ways can you make a square from some of the pieces in the tangram? In how many different ways can the conditions of a theorem produce the same outcome? Again, a perfect example, which we dealt with in a previous video, the angle at the center, twice the angle in circumference. In how many different ways can those conditions in the theorem be arranged? How does the outcome change? It's a big idea in maths, and it's also a habit of mine. We're getting to that. Well, tangents always have an orthogonal relationship with geometric figures. Now, here's a language fixer. They don't have a perpendicular relationship. The relationship is called orthogonal. They are perpendicular to one another. And the consequence of that is where they meet, a right angle is formed. Those three things exists in a discourse on different levels. The relationship is orthogonal. They are perpendicular to one another, meaning there's a right angle formed at the point where they meet. You can see the development here, so that when the word orthogonal pops up in mathematical discussion, it's a relationship we're talking about. So there's an example. The following rhombi are incomplete. Construct the complete figures. Look at what they're doing. What do those two partially shapes need for the minimum and sufficient conditions so that it can be a rhombus or a rectangle, or whatever the question is asking us to do? Okay, so using the newly found properties of the rhombus, students should be able to work backwards and sketch the rhombus based on the knowledge they've gained prior to the activity. We move to the last phase of learning, the phase of integration. The cumulative knowledge gained by completing the instructional cycle now forms the basis for the information phase for the next level of thinking, geometric reasoning. Okay, so we've gone through level 1 or level 2 or level 3, and that whole process now forms the basis for the information seeking at the next level of reasoning. So integration also takes everything that happened at this particular level of reasoning, whether it be in algebra, whether it be in trigonometry or geometry, and it puts it together as a coherent whole of new knowledge that informs thinking when we learn about new concepts, when we reason at a new level of geometric reasoning. Opportunities are given for students here to pull together their knowledge and reflect on it as a whole. Metacognitive processes is what's activated here. Thinking about our thinking and about what it is that we've just learned, and storing it somewhere in the cognitive registry for later learning. The symbols have lost their visual content at this point and are now reorganized by their properties. That's Pierre van Hiele's words as he said it. Learners summarize and integrate what they have learned, developing a new network of objects and relationships to draw from. I often, when I teach, call that my mathematical toolbox. I now know what this tool is able to do for me, so it, with all its dense semantic properties go into my toolbox, and when I need something, it activates, oh, but that tool can do it, I can now use it. That means the knowledge gained through this phase and at this level of reasoning is fully flexible and fully integrated as a coherent whole. So summarize and memorize the properties of a rhombus would be a good activity here to engage in, because now if I talk perpendicular diagonals, immediately the concept image come in the child's head. That could be perpendicular diagonals, could be a kite, could be a square, could be a rhombus. Okay, we want them to think like that, and that is what the purpose is at the integration phase. They should be able to express and summarize what they've learned in some way. Example, small groups of children can design charts, class books, and displays that present what they've learned about the tangram shapes. That's in the lower grades. Small groups, pairs of students or individuals can assign design presentations, poster, flashcards, class books, technology-aided stuff that they design, lists of properties about what they have learned. This will help students, therefore, to logically organize their knowledge of properties of the shapes and explore different shapes relationally and flexibly. Okay, so there's our levels again. A learner may need to cycle through some of the 5 phases more than once with a particular topic, is what the Van Hieles are warning us about. Okay, so I'm going to finish off this video with another quote from Pierre van Hiele. And I find this quote powerful, folks. Children whose geometric thinking you nurture carefully will be better able to successfully study the kind of mathematics that Euclid created. Now remember, in a previous video, I spoke about the importance of constructions in the geometry classroom. Very, very important. Don't just go through it. That activates the relational thinking. Whether it's constructions at grade 8 or at grade 12 using geometric software, it affords the learner the opportunity to go through the process that Euclid did when he constructed with a straight edge and a stick in the ground, constructed relationships, and based on those relationships that were constructed, could formulate the geometric thinking as we know it today. So please afford your learners the opportunity to go through each level very carefully, through guiding them and through activating their thinking and reasoning skills, their relational understanding through the 5 phases of learning. Okay, I hope you learned something from this video. If you did, like it, share it, comment in the space below, and subscribe to my channel so that you can get updates when I post something new.